All right, let's talk about one of the biggest, most important laws in all of physics, the conservation of energy. But we're not going to do it with a bunch of dense equations. Nope. We're going to do it with a story from the one and only Richard Feynman, a guy who was an absolute genius at making the complicated stuff feel simple. So let's just dive right in.
What if I told you that this huge, universal law, the one that controls everything from a simple chemical reaction to the explosion of a supernova, could be totally understood by thinking about a kid's playroom? That's exactly the setup Feynman gives us. It all starts with a story about a boy and his toys.
Okay, so picture this. Feynman asks us to imagine a kid named Dennis, and Dennis has this set of toy blocks. The most important thing about these blocks, they are completely indestructible. You can't break them, you can't split them, that's rule number one.
And here's the magic number. At the beginning of every single day, Dennis has exactly 28 blocks. This number is the one constant, the one anchor in his otherwise messy and chaotic room.
So every evening, his mom comes in to tidy up, and she starts to notice something. No matter what a disaster the room is, when she gathers up all the blocks and counts them, there are always 28. It's like she's discovered a phenomenal law of nature for her own little universe.
But then, of course, one day, disaster strikes. Well, okay, her law seems to be broken. She counts and she only finds 27 blocks. The system isn't perfect. A block is missing. So what does she do? She doesn't throw out the law. She investigates.
And after a little searching, aha! She finds the missing block hiding under the rug. The law is safe. The next day, two are missing, but she sees the windows open, and sure enough, there they are, out in the yard. She realizes she just has to expand her definition of the system to include places outside the room. Now, this is where it gets really interesting. One day, some blocks are missing, and they're not under the rug, they're not outside. But she notices a locked toy box, and Dennis, being a typical kid, absolutely will not let her open it. So now what? How can she check her law if she can't even see all the pieces?
Well, she's a clever mom. She comes up with a brilliant workaround. She weighs the empty box beforehand, it's 16 ounces, and she knows each block weighs 3 ounces. So now she doesn't need to open it. She can just weigh the box, subtract the weight of the box itself, divide by 3, and bingo, she knows exactly how many hidden blocks are inside.
And over time, her formula just gets better. Dennis starts hiding blocks in the dirty bathwater. So she adds another term to her equation based on how much the water level rises. You see what's happening? She has a growing list of calculations for visible blocks, blocks in the box, blocks in the water. But the key is, when she adds all those numbers together, the total is always 28. Her law holds. Okay, so a cute story about a kid and his toys. What does any of this have to do with the fundamental nature of the cosmos? Well, this is where Feynman pulls back the curtain and shows us the big picture.
And here it is, the punchline, the absolute kicker to this whole analogy. The most important lesson you have to take away from this story is that in the real world, there are no blocks. Energy isn't a thing. It's not some little particle we can count. It's an abstract idea, a number we calculate from a formula, just like the number of blocks in that locked box.
So this is what the law of conservation of energy really says. It's a mathematical rule. It says there's this number, and we call it energy. And no matter what happens, no matter what chaotic, incredible changes happen in nature, when we run all the calculations for all the different forms of energy and add them up, that final number stays exactly the same. It is a constant.
So just like Dennis's mom had to discover the formulas for hidden blocks in the box or in the water, physicists over the centuries have had to discover the formulas for all the different forms energy can take.
And the connection is actually pretty direct. Those blocks the mom could see and count easily, that's kind of like kinetic energy, the energy of things that are moving. And the hidden blocks, the ones she had to calculate, that's like potential energy, stored energy, like the energy in a stretched rubber band or a weight held up high.
And oh boy, the universe's full equation for energy has way more terms than the mom had to deal with. We've got gravitational energy, heat, electrical, chemical energy, all the way up to the big one that Einstein figured out, that mass itself is just another form of energy. Each one is a different term in one giant cosmic calculation.
So how on earth did we discover all these weirdly specific formulas? Well, Feynman shows us that sometimes you don't even need an experiment. You can figure it out with pure thought. Just by assuming one simple thing is true, you can't get something for nothing. Perpetual motion is impossible.
Okay, follow the logic here, because this is cool. Let's assume you could build a machine that's better than theoretically perfect.
As you can see here, you could hook it up to a perfect machine in a clever way, creating a cycle that gives you free energy. It lifts a weight for nothing. But we already agreed that's impossible. So if the conclusion is impossible, this starting idea must be wrong. No machine can be better than perfect.
And from that one single logical deduction, the exact formula for gravitational potential energy just falls right out. It has to be weight times height. It's a law of nature that we discovered just by thinking it through, without ever dropping a single apple. It's amazing.
All right, so this is all very elegant and abstract. But what does it actually mean for us here in the real world? Why is this single law so incredibly important?
Well, for one thing, it's the ultimate cleanup tool for physics. Instead of needing to memorize hundreds of separate, complicated rules for how levers and pulleys and gears all work, you just need this one single principle. They're all just different ways of moving energy around. They never create it, they never destroy it, the total always stays the same.
But there is a very important catch, a little twist. While the total amount of energy in the universe never changes, the amount of useful energy, well, that's a different story. The oceans have a mind-boggling amount of heat energy, but it's all disorganized and low-grade, so we can't really use it to, say, power New York City. That's a story for another day, called the law of entropy.
But the amount of energy that is locked away just waiting for us to figure out how to use it is absolutely staggering. I want you to just look at this number for a second. 150 gallons. Doesn't seem like much, right?
But according to Feynman, if humanity could ever truly master thermonuclear fusion, the mass energy locked inside just 150 gallons of regular old water flowing every minute would be enough to power the entire United States. The potential is it's almost beyond comprehension.
And that leaves us with this final thought. The conservation of energy isn't a limitation, it's just the rule book for the game we're playing. The total number of blocks will never change. Our great challenge and our greatest opportunity is to just get smarter and smarter about how we change them from one form into another. So, what's our next move?